Hi everybody, my name is Elena Umili and I'm going to present neural reward machines. So neural reward machines is a framework developed by me, Francesca Argenziano and Roberto Capobianco from Sapienza University and Sony AI. So the framework addresses the problem of reinforcement learning with non-markovian tasks. So when a task is non-markovian, this means that the agent cannot solve it by looking only at the last state and action, but it has to observe the entire state action sequence in order to solve the task. An example of this is shown in the red box. So here we have, for example, an agent inside a real world, and the task is the following. It has to collect the Pcache, then collect the gem, then go to the door, while always avoiding the lava. So this task can be formulated in linear temporal logic over finite traces, so with the following formula. Here, the F, X, and G are temporal operators, while Pcache, gem, door, and lava are prepositional symbols. And this formula can be translated into this automaton, this equivalent. So in order to solve this task, the agent has to know the LTLF formula and the so-called symbol grounding function. So a function that maps the observation the agent sees in the environment into the truth value of the propositional variables we have in the formula. So Pcache, gem, door, and lava. So the main approaches to non-markovian RL are here in the light blue box, and they are the following. The first one is purely based on deep learning. So we have a neural network, typically we got a neural network, an NRM, which reprocess the sequences of state and actions and start adding the representation for the state. This representation is not guaranteed to be Markovian, but in practice, generally it works. And the advantage of this approach is that it does not require any prior knowledge in order to work. The other approach is instead purely symbolic, is the popular reward machine approach, when we have the state of the environment, which is augmented with the state of the DFA. And this new state representation is guaranteed to be Markovian, but it requires prior knowledge of both the symbol grounding function and the temporal specification, so full prior knowledge. Neural reward machines, our approach, are an extension of reward machines to non-symbolic environments for which the symbol grounding function or the temporal specification can be unknown. In the violet box, we have the methodology. We define neural reward machines basically as a probabilistic relaxation of reward machines. So we have an environment state space S, the automaton alphabet P, the automaton state space Q, the set of possible reward values R, the automaton initial state, and then we have the automaton transition function, the reward function, and the symbol grounding function. The difference with reward machines is that these three last functions are all probabilistic. So this framework can be implemented with neural networks, as you see here. And this framework can be used both for reasoning and learning. In case of reasoning, we write in the neural network the parameters associated with the prior knowledge that we have, and we use to predict the next state of the DFA and the next reward. In case of the learning step, we may have partial or incorrect information about these models, and we learn the model parameters from data. So in the yellow box, we have the experiments we did. In the experiments, we assume to know the DFA, but and to not know the symbol grounding function. In particular, the yellow line is the reward obtained by the approach based only on neural network, so on recurrent neural networks. The blue lines, it's our approach, and the green line are reward machines. So as you can see, our approach significantly outperforms the purely deep learning based approach, and is able to achieve nearly the same performance of reward machines, even if it's not using the knowledge of the symbol grounding function. So this means that the prior knowledge it possesses, it can be exploited effectively, even if it's incomplete. So this is all from my side. This paper will appear on the ICAI 2024 proceedings. So if you want to read the paper, you can find the preprint on arXiv.